There's a star in the southern sky you can see with your own eyes. It's the third brightest star you can see at night, a steady amber white point hanging low over the horizon if you're south of the equator. Its name is Alpha Centauri, and it is the closest star to Earth that isn't our own sun. And yet, if you and every person who has ever lived pooled our entire civilizational effort into reaching it, we could not get there. Not in our lifetimes. Not in our children's lifetimes. Not in 10,000 generations of children's lifetimes. The nearest star is 4¼ light years away. At the speed of our fastest spacecraft, that journey would take longer than human beings have existed as a species. This is a story about how close the closest is. About a star we can see and a distance we can't cross. About what 4 light years really means, what lies inside that gulf, and what it feels like to stand on this small planet, knowing that the nearest other sun is both right there and completely out of reach. If you find yourself drifting off to these quiet cosmic distances, hit like and subscribe to Cosmic Drift. Now let us drift outward into the dark and look toward the nearest light. In 1839, at the Royal Observatory at the Cape of Good Hope in South Africa, a Scottish astronomer named Thomas Henderson finally allowed himself to publish a number he had been sitting on for 6 years. The number felt too large to be true, even to the man who had measured it. He had worked it out from a series of careful observations made in the early 1830s, long nights spent at a transit instrument tracking the position of a bright southern star against the background of much fainter ones, watching for the tiny annual wobble that the Earth's movement around the Sun would impose on anything close enough to shift in response. The wobble he eventually found was small, vanishingly small, less than a single second of arc, which in astronomical terms is something like the width of a coin seen from the other side of a large city. But from that tiny wobble, he could compute a distance. And the distance was so staggering that he had withheld it for years, doubting his own instruments, doubting his own work, letting a German astronomer named Friedrich Bessel publish the first confirmed stellar parallax in 1838, while his own earlier measurements still sat unpublished on his desk in Edinburgh. When Henderson finally did release his number in 1839, he had the strange honor of having been first to observe and second to publish. Alpha Centauri was in a sense the first star whose distance humans ever truly measured, but Henderson's hesitation cost him the credit. The number itself is what I want to hold on to for a moment, because once you know what a light year really is, the number does not get smaller, it gets larger. It keeps revealing new ways of being large every time you think about it. Let me walk you through what a light year actually means, because the phrase gets thrown around so often in popular astronomy that it can start to sound like a generic cosmic unit, the way mile sounds like a generic Earth unit. The phrase is not generic at all. It refers to one of the stranger and more specific measurements we have, and understanding what it contains will let the rest of this story land properly. A light year is the distance that light travels in 1 year. That is the whole definition. No complications. Light moves through empty space at a little over 186,000 miles every second, which is roughly 300,000 kilometers a second, depending on which system you grew up in. At that speed, light covers about 5.88 trillion miles in a single Julian year, or roughly 9.5 trillion kilometers. Either way, it is a number your mind does not really hold. You can say it, you can write it down, you can nod at it, but you cannot actually feel 5.88 trillion miles. The imagination stops short of numbers that large, so we have to use smaller units to understand the larger ones, and the best way to do that is to climb a small ladder. Start here on Earth. Start with light moving in an environment you know. When you turn on a flashlight in a dark room, the photons from the bulb reach the far wall in less than a nanosecond. When you flip a light switch, and the whole room brightens at once, that is light filling the room at a speed so high that you cannot detect any lag between the click and the illumination. For anything in your ordinary daily experience, light is effectively instantaneous. It gets where it is going before you can notice it has left. Now step outside, walk under the sky at night and look at the moon. The moon, as you know, is about 240,000 miles away, give or take. It is close enough that we have sent people there and back within a week. Close enough that a radio signal from a lunar lander reaches Earth in about 1 1/3 seconds. If you stood on the moon's surface right now and someone on Earth waved to you, the image of that wave would reach your eyes just over a second after it happened. That is the first stop on the light-year ladder. The moon is 1 light second away roughly. The fastest information in the universe takes a second to cross the gap between us and our closest natural neighbor. Now go further. Look at the sun, which of course you cannot look at directly, but imagine looking at it from a safe distance. The sun is about 93 million miles away. That is a long way by any human measure. Commercial airliners would need years to cover that distance if they flew without stopping. The fastest spacecraft we have ever launched take months to get anywhere near it. And yet, in terms of light, it is not far at all. The photons that reach your skin on a summer afternoon left the surface of the sun about 8 minutes ago. 8 minutes. That is how long it takes light at its full unimpeded speed to cross the distance between the sun and Earth. If the sun were to suddenly wink out of existence this instant, you would not know it for another 8 minutes. You would continue to feel warm, you would continue to see sunlight. Your plants would continue to do their quiet photosynthesis, all while no solar light was actually being produced anymore. That is the 8-minute delay between what the sun is doing now and what you can observe it doing. That is our second rung. Keep climbing. Go out past Mars, past Jupiter, past Saturn, past the slow, cold fields of the outer planets. Eventually, you reach Pluto, which at its average distance is something like 3.5 billion miles from the Sun, depending on where in its eccentric orbit it happens to sit. Light from the Sun takes about 4.5 hours to reach Pluto. 4.5 hours. If you were standing on Pluto's frozen nitrogen surface, the sunrise you watched this morning would be showing you a sun that had risen 5 hours earlier by the reckoning of anyone back home on Earth. By the time you saw it, the event that produced that light would already be a long way in the past. Your noon would be the sun's late afternoon. That is our third rung. A few hours of light to cross the widest common definition of our own solar system. Now here is where the ladder starts to stretch. Keep going past Pluto, past the Kuiper Belt, past the outer reaches of the sun's magnetic influence, and light itself keeps traveling mile after mile, hour after hour, day after day, without arriving anywhere in particular. The space between stars is mostly empty. Not perfectly empty, not in any exotic cosmic sense, but empty enough that light can travel for years without being substantially absorbed or scattered. And this is where the light year becomes the unit that matters. Not seconds, not minutes, not hours, but years. Whole calendar years of photons moving at their maximum physical speed through the dark covering distances so large that they require the calendar itself as a ruler. Alpha Centauri sits 4.25 of those years away. More precisely, the 3-star system sits between about 4.2 and 4.37 light years from Earth, depending on which of its 3 members you choose to measure to. its closest component, a faint red dwarf called Proxima Centauri, is the nearest of the nearest at 4.2 light-years. Its two brighter members, Alpha Centauri A and Alpha Centauri B, form a binary pair a little farther out at about 4.37. Either way, the light you see tonight from any of these stars left them during a time when the world you live in was substantially different from the world it is now. 4 years ago, if you think back, you were a slightly different person, with slightly different concerns, living in a world with slightly different news, and the photons you can potentially see tonight from Alpha Centauri began their journey toward your eyes back then. They have been traveling continuously ever since. That in one sentence is what a light year means. It means that every act of looking at a distant star is an act of looking into the past. For Alpha Centauri, you are looking at a little more than 4 years ago. For more distant stars, you are looking at longer stretches. For galaxies, you are looking across millions or billions of years. The universe from our vantage point is not a snapshot. It is a layered recording with different layers arriving at different times, each one carrying news that is already old when it arrives. Alpha Centauri is by the standards of the larger cosmos practically next door. 4.25 light-years is for a galaxy nothing. Our galaxy is 100,000 light-years across. The Andromeda galaxy sits 2.5 million light-years away. The deepest images from the James Webb Space Telescope show galaxies whose light has been traveling for over 13 billion years. Against those distances, 4.25 is a whisper. It is basically the doorstep. And yet, it is also further than anything we can cross. That is the paradox I want to sit inside with you for the rest of this drift. The closest star to our Sun is both close in any galactic sense and completely unreachable in any human sense. It is visible to our naked eye. It has planets of its own, one of them roughly Earth-massed. It is an object we know quite well in terms of stellar physics and broad properties. But no human will ever stand on any of its worlds, and no instrument we currently know how to build can carry a payload there in a single human lifetime. 4.25 light-years is the outer edge of our neighborhood and the inner limit of our reach at the same time. Before we go further, I want to name the 3 stars of the system properly, because Alpha Centauri is actually a single name that refers to an ensemble, not a single body. The system contains Alpha Centauri A, a sun-like yellow star, roughly the same mass and temperature as our own. It contains Alpha Centauri B, a slightly smaller, slightly cooler, orange-yellow companion that orbits A in a long elliptical dance. And it contains Proxima Centauri, a small dim red dwarf, far dimmer than either of its brighter siblings, sitting much farther out in the system, gravitationally bound to the AB pair, but orbiting them so distantly that its full orbital period is measured not in years, but in hundreds of thousands of years. 3 stars, one system, all gravitationally related, all sharing a slow tumble through the same region of the galaxy, and all of it only visible from the southern hemisphere. If you live in North America, in Europe, in most of Asia, you cannot look up and see Alpha Centauri at all. It is too far south in the sky. The horizon hides it. You have to be below about 30 degrees north latitude to glimpse it, and really, you have to be well south of the equator to see it clearly. This is why Henderson had to go to the Cape of Good Hope to measure it. It is why so much of the early work on the system came out of observatories in South Africa, Australia, and Chile. The nearest star to Earth is for much of humanity's history below the horizon. A star we know about mostly by reputation. A star most people on the planet have never actually seen. Unless you have traveled south of your usual latitude at some point in your life, there is a good chance you have never laid eyes on Alpha Centauri. You know about it from books and films and documentaries. You know its name. You know it is there. But you have never looked up at it yourself and registered the fact that this particular bright dot is our nearest stellar neighbor. Most of our species lives under skies where the nearest star is hidden, which is, when you think about it, a strange fact on its own. The closest other sun in the cosmos is for the majority of humans permanently out of view. That hiddenness is where we are going to start. From Henderson at the Cape straining to measure a wobble he barely believed in. From the fact that the nearest other sun can only be seen from the southern half of the planet. From the long ladder of light seconds to light years that carries us outward from familiar distances into a distance that does not really admit of being crossed. Let us walk slowly now from what the three stars actually are out through the planets they carry with them, and into the full scale of the emptiness that separates those worlds from ours. Alpha Centauri A is in most ways that matter a sibling of our Sun. It is a yellow dwarf of a type astronomers call G2, which is the same classification the Sun carries. Its mass is roughly 1.1 times the Sun's mass. Its luminosity is about 1.5 times the Sun's luminosity. Its temperature is a few dozen degrees warmer. Its color seen up close would be the same steady, warm yellow-white that our Sun would display if you could view it from any reasonable distance. If you replaced our Sun with Alpha Centauri A tomorrow, life on Earth would notice the difference only in small technical ways. The sky would look nearly the same. Photosynthesis would proceed normally. Mornings would still feel like mornings. The star is that close to being a twin. What makes it not a twin is age and the details of what it is doing right now in its long stellar life. Alpha Centauri A is probably a little older than the Sun. Some estimates put it at around 5 or 6 billion years old compared to our Sun's 4.5 billion. It is in a similar phase of stellar evolution, still fusing hydrogen into helium in its core, still enjoying the long, stable middle stretch of its life, before the eventual swelling and cooling that will come when its core hydrogen runs out. That eventual ending is for now distant. Alpha Centauri A has a few billion years of steady, stable burning still ahead of it, just as our Sun does. Both stars will end in roughly the same way, expanding into red giants, shedding their outer layers, settling into quiet white dwarfs. But not for a long time yet. Alpha Centauri B is the smaller partner in the binary pair. It is a K-type orange-yellow star, slightly less massive than the Sun, slightly cooler, slightly dimmer. About 90% of the Sun's mass. About half the Sun's luminosity. It would still be recognizable as a Sun if you saw it from a planet, just a slightly warmer, slightly dustier looking one. K-type stars have a particular appeal for astronomers interested in habitability because they tend to be long-lived and relatively calm, giving any planets around them extended periods of stable conditions. Alpha Centauri B, specifically, is probably several billion years old, similar to its larger companion. The two stars orbit each other on a long elliptical path, swinging in toward each other to within about 11 astronomical units at their closest approach, and then swinging back out to around 36 astronomical units at their farthest, with an orbital period of roughly 80 Earth years. 80 years for one full dance of A and B around their common center of mass. That is one of the quietly beautiful facts about the system. The two sun-like stars are not moving past each other, not drifting in random directions, but orbiting each other. They are a couple. They have been gravitationally bound to one another for billions of years swinging in their long, slow waltz, and they will continue doing so for billions more. Anyone watching the Alpha Centauri system from a distance across enough time would see the two stars trade positions slowly in the sky, sometimes wider apart, sometimes closer together, always returning to the same basic choreography. Then there is the third member, which is a genuinely different kind of object. Proxima Centauri is a red dwarf. Technically an M-type star, much smaller and much fainter than either of its brighter companions. Its mass is only about 1/8 of the Sun's. Its luminosity is a fraction of 1% of the Sun's. It is so dim that despite being the closest star to Earth, it is invisible to the naked eye. You cannot see Proxima Centauri from your backyard, no matter where you live. You need a telescope. The star that holds the title of nearest is in plain human vision, not there at all. Alpha Centauri AB is what you see when you look at the bright amber-white point in the southern sky. Proxima is a faint red ember, hiding nearby, identified only in 1915 by a Scottish astronomer named Robert Innes, who was looking for exactly this kind of faint companion to the brighter pair. Proxima sits much farther from AB than A and B sit from each other, roughly 13,000 astronomical units out, which is about 1/5 of a light year. At that distance, its gravitational connection to the AB pair is tenuous. It takes Proxima hundreds of thousands of years to complete a single orbit around the binary center of mass. If you watch the system over a single human lifetime, you would see the AB pair do almost an entire orbit of each other, with Proxima barely moving in the background. The red dwarf drifts so slowly around its brighter siblings that for all practical timescales of observation, it is essentially stationary relative to them. But gravitationally speaking, it is part of the family, and Proxima, despite being dim, has an outsized importance to us. Because Proxima is the closest of the three, a distinction worth honoring, given how close everything in this system already is. It sits at about 4.24 light-years from Earth, compared to Alpha Centauri A and B at 4.37. That difference of roughly 0.13 light-years, something like 40,000 astronomical units, makes Proxima the single closest known star to the Sun that is not the Sun itself. Hence, the name. Proxima Centauri means nearest Centauri, and the word Proxima in Latin means nearest, the star that was named quite literally for being the closest. Now let me widen the frame for a moment and talk about what Sun-like actually means to astronomers, because the phrase gets tossed around in ways that obscure what it really describes. A Sun-like star is a G-type main sequence star, roughly between 0.8 and 1.2 times the Sun's mass, with a surface temperature between about 5,000 and 6,000 Kelvin. That definition is narrower than it sounds. Most stars in the galaxy do not meet it. The overwhelming majority of stars by number are much smaller and cooler than the Sun. Red dwarfs like Proxima make up perhaps 3/4 of all stars. The bright blue giants you see prominently in deep space photographs are numerically rare. The Sun sits in a particular middle zone of the stellar classification, neither the brightest nor the faintest, neither the most massive nor the least. It is average in a technical sense, but not statistically typical. Typical stars are smaller and dimmer. The Sun is larger and brighter than most of its galactic neighbors. Alpha Centauri A is among the stars most like the Sun, in the broader neighborhood the closest. That is one of the reasons the system has been studied so intensely for so long. If you want to understand what Sun-like stars do outside our own solar system, and you want data that is clear and close and well resolved, Alpha Centauri A is your best available target. its light is bright enough to analyze in fine spectroscopic detail. Its geometry is stable enough to track its orbital dance with B over decades. Its age and composition are well constrained by multiple independent measurements. When astronomers want to study a G-type main sequence star that is not our own, they almost always start here. Which raises a question that has been implicit throughout this whole description, and that I want to make explicit now. Could there be planets around Alpha Centauri A or B, in addition to the planets we already know exist around Proxima? The answer, as of our current understanding, is yes. At least one strong candidate around A, which we will come to in a later section. Possibly more still undetected. The system has been a priority target for exoplanet searches for decades, precisely because finding planets around the nearest stars is easier in principle than finding planets around more distant ones. The signals are stronger, the noise is relatively lower, and any world we find there, however modest, becomes automatically one of the most important objects in observational astronomy. Not because it is special in its own right necessarily, but because it is nearby. Proximity confers scientific value. Close targets are studiable targets. Before we get to the planets, though, I want to stay with the three stars themselves for another few minutes, because the triple nature of the system is itself one of the more interesting facts about it. Many stars in the galaxy are binaries or triples. Single stars like the Sun are not, as far as we can tell, a majority. Large surveys suggest that roughly half or more of all stellar systems contain more than one star. The Sun's loneliness may be more the exception than the rule. Most stars have company. Alpha Centauri is one of the closer examples of that general truth. It happens to be our closest stellar neighbor, and it happens to be a triple. Those two facts taken together remind us that stellar systems more complex than our own are perfectly ordinary. What does living in a triple system actually look like in terms of sky and daylight and seasons? If you were standing on a planet orbiting Alpha Centauri A, at a distance comparable to Earth's distance from the Sun, you would see your primary star looking much like the Sun looks from Earth. A bright, warm yellow disk rising and setting, driving your weather and your plant growth. But you would also see Alpha Centauri B, the smaller orange companion, depending on where A and B were in their 80-year mutual orbit, either as a blazing bright separate point of light, or as a close-second sun visible during the day, or as a very bright star visible at night. Over the 80-year cycle, B would move closer and then farther from A in your sky. Sometimes B would be a dominant nighttime presence, the brightest thing in the night sky by a wide margin. Sometimes B would be too close to A to be easily distinguished, lost in its partner's glare. And Proxima, off in the far distance, would be too dim to notice with the naked eye. The daylight itself on such a planet would depend on the geometry at any given moment. During parts of the 80-year cycle, when A and B were well separated from each other, as seen from your planet, you would have one main sun and one bright secondary in your sky. During other parts, when the two stars were near conjunction, you would have them effectively overlapping and functioning as a single bright source. Your climate would track these slow variations in ways that might or might not allow stable long-term conditions. Whether planets in binary systems can support stable climates over evolutionary timescales is in fact one of the open questions in astrobiology. It depends on the specific geometry, the planet's orbital radius, and how the extra heat from the companion star interacts with whatever atmosphere the planet has. Around Proxima conditions would be dramatically different. You would have your primary star, the small red dwarf, looking larger and closer in the sky than our Sun looks from Earth, because any habitable zone planet around a red dwarf has to be much closer to it than Earth is to the Sun. The star would appear dimmer in intensity, redder in color, and larger in apparent size than our Sun does to us. Days and nights on such a planet would likely not exist in the sense we mean them, because red dwarf habitable zones tend to produce tidally locked worlds with one face permanently turned toward the star and the other permanently in shadow. The sky above any such world would show a permanent red sun on one side of the horizon. The sky on the other side would show darkness, and very far away, the two much brighter points of light that are Alpha Centauri A and B, the closest neighbors from Proxima's own perspective. Those two stars would be the brightest objects in Proxima's night sky, by a large margin outshining everything else. And yet, even they would be from the vantage of a Proxima-bound world, just distant points of light. Too far to visit, too close to ignore. These three stars in their strange triangular arrangement are what we mean when we talk about the Alpha Centauri system. They are the whole thing. Everything else about the system, including the planets, is subordinate to this triple stellar structure, this long, slow gravitational choreography that has been going on for billions of years and will continue for billions more. When Henderson measured his parallax in the 1830s, he did not yet know the system was a triple. Proxima would not be identified for another 75 years. What Henderson saw was a single bright point in the southern sky, bright enough to be the third brightest star visible from Earth, close enough to show a measurable parallax nearby, enough to shift against the more distant stars as Earth moved around the Sun in its annual loop. That shift, that measurable wobble, was enough to crack open the cosmic distance scale for the first time. It was enough to tell humanity that even the nearest star was impossibly far. The word impossibly is going to come back over and over in this story. Not because the distance is impossible to measure, because we have been measuring it with increasing precision for nearly 2 centuries now, but because the distance is impossible to cross, possible to see, possible to study, possible to know a great deal about, not possible to visit. That asymmetry between what we can know and what we can reach is the shape of our relationship with Alpha Centauri. And it began as most astronomical relationships begin, with a single measurement that no one quite believed at the time it was made. That shift the tiny annual wobble Henderson spent months teasing out of his data is what astronomers call parallax. It is one of the more elegant measuring techniques in science, and it rests on a principle so simple you can demonstrate it to yourself right now, sitting wherever you are. Hold one finger up in front of your face at arm's length. Close one eye, then the other, alternating back and forth. Your finger against whatever is behind it appears to jump from one side to the other with each eye. The finger has not moved. Your eyes have not moved. What has changed is your vantage point by a few inches. And that small change of vantage point produces an apparent shift in where the finger seems to be against the more distant background. Now imagine doing that same experiment, but with a much larger baseline between your two eyes. Instead of the few inches between your actual eyes, imagine a baseline of, say, 100 miles. Your finger held at arm's length would appear to jump by a tremendous amount against the background when you shifted between those two widely separated vantage points. Now imagine making the finger farther away, say several feet in front of you instead of at arm's length. The apparent jump would be smaller because the finger is closer to the background relative to the baseline. The farther your finger is from you for a fixed baseline, the smaller the jump. That is parallax in its simplest form. A known baseline, combined with an observable apparent shift, lets you compute the distance to the object doing the shifting. It is the method surveyors have used for centuries to measure distances they could not walk across. And it is the method astronomers eventually figured out how to apply to the stars. The baseline for stellar parallax is the Earth's own orbit around the Sun. Twice a year, the Earth is on opposite sides of that orbit, separated from its position 6 months earlier by about 186 million miles. That is a very large baseline, larger than any single measurement that could be made from one fixed location on the Earth itself. If you measure the apparent position of a star in January, and then measure its apparent position again in July, and the star is close enough to us, its position will have shifted very slightly against the more distant stars that form the background of the sky. That shift, that parallax combined with the known baseline of Earth's orbital diameter, gives you the distance. The trouble is that the shift for real stars is tiny, fractions of a single second of arc. Imagine dividing a full circle around the horizon into 360 degrees, then dividing each degree into 60 minutes, then dividing each minute into 60 seconds. 1 second of arc is already an extraordinarily small angular measurement. Most stars, even the closest ones, shift by less than that over the full span of a 6-month baseline. You are measuring the apparent position of something to within a tiny fraction of what the unaided eye can resolve, and you are doing it with instruments that, in the 19th century, were built out of brass and glass and human patience. This is why stellar parallax took so long to actually achieve. The method was understood in principle for centuries before anyone could actually measure one. Galileo in the 17th century was already talking about parallax as the thing you would expect to see if the Earth really did orbit the Sun. Tycho Brahe, working in the late 16th century, famously argued against heliocentric models, in part because he could not detect any parallax in the stars, which he thought implied that either the Earth was not moving or the stars were impossibly distant. Tycho leaned toward the former conclusion. He was wrong about which, but he was right about the dichotomy. Either the Earth is not moving or the stars are very far away. Once the Earth's motion was firmly established, the very far away part became the inescapable conclusion. Nobody for a long time could actually measure the distances in question. Between Galileo and Henderson, more than 2 centuries of astronomy passed without a single successful parallax measurement of a star. People tried many times over with competing astronomers at competing observatories using competing methods. Most claims of stellar parallax in that period turned out to be wrong, driven by instrumental errors rather than real celestial motion. The problem was not the theory, the problem was the precision. You needed instruments accurate enough to detect a fraction of a single arcsecond, and such instruments did not exist until the first decades of the 19th century. Let me pause here on the texture of what astronomers thought stars even were during that long period of uncertainty, because it adds something to understanding why Henderson's measurement mattered. Aristotle, in his cosmology, had placed the stars on a great crystalline sphere rotating around the Earth at some unknown but finite distance. Ptolemy refined that picture without fundamentally changing it. For most of European astronomical thought, the stars were simply lights fixed on some distant surface, all at roughly the same depth, forming a background against which the nearer and more dynamic objects, the planets and the Moon and the Sun, did their various motions. The question of whether the stars were at different distances from us, and whether some were much closer than others, did not really arise until after Copernicus suggested that the Earth was itself a planet orbiting the Sun. Once the heliocentric model took hold, and it took hold slowly over the course of the 17th and 18th centuries, the question of stellar distances became urgent. If the Earth is moving around the Sun, and we see no parallax in the stars, then the stars must be very far away. Just how far away was the unanswered question? Some astronomers guessed, others tried to measure, and nobody succeeded for 200 years. Stars during that long stretch were understood in broad terms as distant suns, similar in nature to our own, but at unknown distances that could only be guessed at through indirect arguments, through brightness comparisons, through the statistics of motion across the sky. That is the background against which Henderson, in the early 1830s, began his observations at the Cape of Good Hope. The southern sky was less well mapped than the northern sky, because most European observatories sat at northern latitudes and could not see the deep southern constellations. Henderson had been appointed to the Cape specifically to fill that gap, and it was pointed out to him while he was there that one particular southern star, Alpha Centauri, showed a large proper motion. Proper motion is the actual drifting of a star across the sky over years separate from the annual wobble of parallax. A star that has a large proper motion is usually a star that is relatively close to us because its actual motion through space subtends a larger angle from our vantage point when it is nearer. Alpha Centauri's proper motion was large enough to suggest that the star was one of the closer ones, and therefore a good candidate for parallax measurement. So Henderson measured. Between April of 1832 and May of 1833, he took repeated precise positional observations of Alpha Centauri against the background stars. He returned to Scotland in ill health. He began to analyze his data. The parallax he computed was about 1 arcsecond, which when translated into distance implied that Alpha Centauri was roughly 1 parsec away, or about 3¼ light years. Modern measurements put the actual distance at about 4¼ light years, so Henderson's first value was something like 25% too small. But it was by any reasonable judgment correct in order of magnitude. It told him that Alpha Centauri was a few light years away, not a few hundred, not a few thousand, not at the fantastic distances that some earlier cosmologies had imagined. It was a real concrete finite number on a real concrete finite scale. I should pause for a moment on the word parsec because it is one of those astronomical units that has become part of the general vocabulary through science fiction, without most people knowing what it actually means. A parsec is the distance at which an object would show a parallax of exactly 1 arcsecond when observed from opposite sides of Earth's orbit. The name comes from parallax of 1 arcsecond shortened into something pronounceable. It is a strange and specific unit defined entirely in terms of the parallax measurement technique itself, which means it is the most natural unit in which to express stellar distances when you are doing parallax astronomy. 1 parsec is about 3¼ light years. Alpha Centauri sits at about 1⅓ parsecs. The next nearest stars, Barnard star and others in our immediate galactic neighborhood, are at a few parsecs. The center of the Milky Way is about 8,000 parsecs away. The unit scales gracefully. Astronomers today still use it for almost any distance measurement within the galaxy, and the even larger kiloparsec and megaparsec for extra-galactic distances. When Henderson computed that Alpha Centauri was just under 1 parsec away, the number he was using referenced a standard that was itself relatively new, and it placed his star at the very inner edge of what parallax astronomy could reach at the time. anything much farther than a few parsecs produced parallax shifts too small for early 19th century instruments to measure reliably, which means that Henderson, Bessel, and Struve, in measuring the parallaxes of the three nearest bright stars they could reach, were operating at the very limit of what was technically possible in their era. Each measurement was a hard-won achievement. Each one opened a tiny crack in the wall separating our solar system from the unknown scales of the larger galaxy. And behind each crack was a realization slowly absorbed by the astronomical community over the following decades that the universe was much larger than anyone had previously dared to estimate. And Henderson, looking at his number, did not publish it. He hesitated. He doubted his instruments. He worried that the earlier failed attempts at stellar parallax by other astronomers meant that his own result would be greeted with skepticism and then overturned. He sat on the data. He worked on other projects. He published a star catalogue. He worked on refraction tables. He pursued the ordinary business of a working astronomer with a new appointment back in Edinburgh as the first Astronomer Royal of Scotland. The parallax number sat in his papers unannounced. Meanwhile, in Prussia, a German astronomer named Friedrich Bessel had been conducting his own parallax campaign, targeting a different star called 61 Cygni. Bessel was a methodical and careful observer, working with a precision heliometer at the Königsberg Observatory. In 1838, he published a successful parallax measurement for 61 Cygni, making him the first person to have publicly measured a stellar distance. The news was substantial. The wall between the Earth and the stars had been cracked open. 61 Cygni, which Bessel had determined to be about 10.5 light-years away, was suddenly a known quantity. The Earth had a measured stellar neighbor. Henderson, stung perhaps into motion by Bessel's announcement, finally published his own earlier measurement of Alpha Centauri in 1839. His observations had been made years before Bessel's. His star was actually closer to Earth than Bessel's, but his hesitation cost him the historical credit. Henderson is in most accounts remembered as the second astronomer to measure a stellar parallax, even though his observations were first and his star was nearer. There is a small lesson in that about the relationship between having data and publishing data, which every working scientist since Henderson has had occasion to think about at least once in their career. What mattered in the longer run, though, was that by the end of the 1830s, human beings had directly measured the distances to two nearby stars. A third measurement soon followed this one of the bright star Vega by a Russian-German astronomer named Friedrich von Struve. 3 stars, 3 distances, a rough picture of how far some of our nearer neighbors actually were. The scale of the cosmos, which had been vague and speculative for most of human history, had become numerical. Stars were confirmed to be at enormously varying distances from the Sun, all of them vastly farther than any object in our solar system, all of them accessible through the same parallax technique if the instruments were good enough and the patience was long enough. Alpha Centauri in particular had become the nearest known star, 3.25 light-years by Henderson's computation, about 4.25 light-years by modern refinements, either way unmistakably the closest, and the fact of its closeness carried with it a certain consolation. If the nearest star was 4 light-years away, then the next nearest was some further distance, and the next some further still, and the general scale of the stellar neighborhood began to reveal itself. A galaxy was not a sheet of equally distant points on some crystalline sphere. It was a 3-dimensional distribution of stars at wildly varying depths, with a few lucky neighbors that happened to be close enough to study, and a vast multitude of others farther and fainter that extended out to what would turn out to be 100,000 light years in any direction. That is the measured universe. It has been the measured universe in broad outline since the 1830s. Every refinement since then has been a matter of precision, not of basic structure. The Gaia Mission, a European space observatory launched in 2013 and still operating as of this writing, has measured the parallaxes of more than 1 billion stars to precision levels that would have stunned Henderson. The Alpha Centauri system in particular has been measured and remeasured many times over. We know its distance to better than a fraction of a percent. We know the positions of all 3 of its stars to within tiny fractions of an arcsecond. What was for Henderson a single faintly trembling dot on a photographic plate is now one of the most thoroughly characterized stellar systems in existence. And all of that work, all of that accumulated astronomy, rests on the method Henderson and Bessel and Struve first successfully applied in the late 1830s. The annual wobble, the finger held up against the background. The idea that if you know your baseline and you can measure a shift, you can compute a distance. It is one of the oldest and most elegant measurement techniques in science, and it has been quietly extending our understanding of the cosmos ever since. What those measurements let us do in the decades that followed was begin to ask more detailed questions about what was actually living in the stellar systems we had identified. Not just how far, but what. Not just distance, but content. And the Alpha Centauri system, as the closest of them, eventually became the most scrutinized of them. When astronomers started searching for planets around stars other than the Sun, the nearest star system was the first and most natural place to look. In August of 2016, a team led by an astronomer named Anglada-Escudé at Queen Mary University of London announced that they had found a planet orbiting Proxima Centauri. The announcement was the culmination of a multi-month observing campaign called Pale Red Dot, named in gentle tribute to Carl Sagan's description of Earth as a pale blue dot, seen from the distant Voyager spacecraft. The Pale Red Dot campaign trained a network of telescopes led by the High Accuracy Radial Velocity Planet Searcher, or HARPS, at the European Southern Observatory in Chile on Proxima Centauri for 2 months in early 2016, monitoring the star night after night for the tiny Doppler shifts that would reveal the gravitational tug of an orbiting planet. The signal they found was small, steady, and persistent. Something was there pulling on Proxima, producing a wobble in the star's motion on an 11-day cycle. That something turned out to be a planet of roughly Earth mass orbiting Proxima Centauri at a distance of about 0.05 astronomical units, well inside what would be the orbit of Mercury in our own solar system. Astronomers call this planet Proxima b, and it is by any measure one of the most important exoplanet discoveries ever made. Not because it is a particularly unusual planet, but because of where it is. The closest star to the Sun has a planet roughly the size of Earth, orbiting at a distance where, given Proxima's much fainter luminosity, the stellar flux striking the planet is comparable to what the Sun delivers to Earth. In the narrowest technical sense, Proxima b sits in its star's habitable zone. The habitable zone is one of those astronomical phrases that deserves careful handling, because it is often misread as a guarantee of conditions that support life. It is not. The habitable zone is a narrow range of distances from a star where all else being equal, a rocky planet with the right atmospheric pressure could potentially have liquid water on its surface. That phrase, all else being equal, is doing a tremendous amount of work in that sentence. all else is rarely equal. The habitable zone is a starting point for thinking about whether a planet might support life, not a finish line. A planet can be in the habitable zone and still be a lifeless wasteland if it lacks the right atmosphere, or if it has the wrong magnetic field, or if its star has the wrong kind of flaring behavior, or if its rotation is locked in a way that produces extreme climate asymmetries. Mars is on the edge of our own sun's habitable zone. Venus is inside the inner boundary. Neither is Earth. Being in the habitable zone means being in the right general distance range. It does not mean being habitable. For Proxima b, the questions of whether it is actually habitable are genuinely open. And most of the open questions trace back to the nature of its parent star, because Proxima Centauri is not the Sun, and red dwarfs do things to their nearby planets that the Sun does not do to Earth. The first issue is flares. Red dwarfs are famously active stars. Their surfaces are full of convection, full of turbulent plasma motion, and they produce frequent bursts of high-energy radiation that can be orders of magnitude more intense than the peaks of our Sun's ordinary 11-year cycle. Proxima Centauri is a flare star. It produces flares regularly, some of them intense by solar standards. A large flare from Proxima Centauri, striking a planet orbiting only a few million miles away, delivers a dose of ultraviolet and X-ray radiation that would be catastrophic for any unprotected atmosphere and for any biology on the surface. Over long stretches of time, repeated flares can strip a planet's atmosphere away entirely, leaving a bare rock baked by stellar radiation. Whether Proxima b has managed to hold onto an atmosphere despite billions of years of this flaring treatment is a question we do not yet have an answer to. We do not know. The second issue is tidal locking. Red dwarf habitable zones sit very close to the star because the star is so dim that you have to be close for the flux to be Earth-like. And planets that orbit close to their stars tend to become tidally locked over time, meaning that the same face of the planet always points toward the star, much like the same face of our moon always points toward Earth. A tidally locked planet has a permanent day side and a permanent night side. The day side bakes under a perpetual red sun. The night side freezes in perpetual darkness. Between them, along the boundary, is a narrow twilight zone where temperatures might be moderate enough for conditions we would recognize as hospitable. Whether life could arise and persist in such an extreme climate is again an open question. It depends on whether the atmosphere can circulate enough heat from the day side to the night side to keep the night side from freezing out entirely. On Earth, atmospheric and oceanic circulation distribute heat efficiently. On a tidally locked Proxima b, whether such circulation would work at all is unclear. Some climate models suggest yes with the right atmosphere. Others suggest no, with slightly different assumptions. The third issue is rotation-related stellar wind. Because Proxima is small and close, and because Proxima b is even closer to Proxima than the Earth is to the Sun, the stellar wind streaming off Proxima hits the planet with much greater intensity than the solar wind hits Earth. Without a strong magnetic field to deflect that wind, the atmosphere of any close-in planet gets stripped over time. Earth is protected by its magnetic field. Whether Proxima b has one is unknown. If it does not, the atmospheric stripping may already have reduced the planet to something closer to Mercury than to Earth. All of these concerns apply equally to the two additional Proxima planets that have been identified since 2016, or proposed as candidates based on subsequent data. Proxima c, proposed in 2019, is a larger planet orbiting much farther out than Proxima b, well beyond the habitable zone with an orbital period of several years. Proxima d, proposed in 2022, is a smaller planet, orbiting even closer to the star than Proxima b, deep inside any reasonable habitable zone, probably too hot for liquid water. The Proxima system, as we currently understand it, contains at least 3 planets. Proxima b is the one in the habitable zone. Proxima c is the distant big one. Proxima d is the small hot inner one. All 3 are interesting for different reasons. None of them, given current knowledge, are confirmed as habitable. That word confirmed matters, because we do not yet have direct images of any of these worlds. They were detected, all of them, through the radial velocity method, which measures the tiny Doppler wobble that a planet's gravity produces in its parent star, rather than through direct imaging or transit photometry. Radial velocity tells you that a planet is there and roughly what its minimum mass is, and roughly how far it orbits, and roughly what its orbital period is. Radial velocity does not tell you what the planet looks like. It does not tell you whether it has an atmosphere or what that atmosphere is made of, or whether there is liquid water or anything else you might want to know about the surface. To learn those things, you need other techniques. You need direct imaging, which attempts to actually see the planet's own light separately from its star's glare. Or you need transit spectroscopy, which catches the light of the star as it filters through the planet's atmosphere during a transit, revealing which gases are present by their absorption signatures. Neither of those techniques has yet worked well for the Proxima planets. Proxima b is a rocky world close to a faint star, meaning it reflects very little light in absolute terms, and what it does reflect is drowned out by the star's own output, unless you can mask the star very precisely. Proxima b also does not transit its star as seen from our line of sight, at least not in any configuration that has let us use transit spectroscopy effectively. For now, we know that Proxima b exists. We know roughly how massive it is. We know roughly where in the Proxima system it orbits, and we know very little else. The questions about whether it has air, whether it has water, whether it has any life, all remain open because we do not yet have the tools to answer them for such a specific and challenging target. What we do have, and what Anglada-Escudé's team did establish, is the existence of a planet in the right general distance range. That is a meaningful result. Before 2016, it was plausible that the nearest star had no planets at all, or only planets that were far too hot or far too cold for life, as we understand it. After 2016, we knew that the nearest star did have a rocky, roughly Earth-sized planet in the roughly right location. That knowledge changes the tone of the conversation about our stellar neighborhood. The closest other sun has a potentially Earth-like world next to it. Whether that world is actually Earth-like in any meaningful sense, we cannot yet say, but it could be. The possibility is on the table. There is one other thing about red dwarfs that is worth lingering on because it cuts in a direction opposite to all the challenges I just listed, and it is one of the reasons astronomers do not dismiss red dwarf habitable zones out of hand. Red dwarfs live a very long time, much longer than sun-like stars. Our own sun will spend about 10 billion years on the main sequence fusing hydrogen into helium, before swelling into a red giant and eventually settling into a white dwarf. Proxima Centauri, by contrast, is expected to continue fusing hydrogen for something like 4 trillion years. Not billion, trillion. That is roughly 300 times longer than the current age of the universe. Red dwarfs burn their fuel so slowly and recirculate their hydrogen so efficiently through convective mixing that they are essentially immortal on cosmological timescales. Proxima Centauri, as we see it today, is barely started. It has almost all of its life still ahead of it. which means that if life ever does take hold on a red dwarf world, and if it survives the flaring and the atmospheric stripping and the tidal lock, it has a vast amount of time in which to develop. Billions of years, tens of billions of years, hundreds of billions of years. Long after our own sun has died and the Earth has become uninhabitable, Proxima Centauri will still be quietly burning, and if Proxima b has life on it, that life will still be going about its business. The long timescales available around red dwarfs are one of the arguments that astrobiologists sometimes make for why life, if it exists elsewhere in the galaxy, may be disproportionately found around these small, patient, long-lived stars. They offer the most time. They are in that specific sense generous hosts, even if the immediate conditions they impose on their planets are challenging. Whether any of that applies to Proxima b specifically, we cannot know from our current vantage point. The planet may be a lifeless ember baked and stripped and battered by flares into a condition that never allowed biology to begin. Or it may harbor something we cannot yet detect, something quietly surviving under whatever atmosphere and ocean it has managed to keep. The tools to answer that question directly are still a generation or two away in terms of our instrumental capabilities. The extremely large telescope currently under construction in Chile may provide the first real atmospheric characterization of Proxima b when it comes online later this decade. Until then, the question remains open, which is in its own way a quiet privilege. We get to keep wondering. The nearest star has a planet that might be alive, and we do not yet know if it is. The wondering itself is free to last as long as we want it to. I want to sit with one more layer of this because it is one of the more poetic aspects of exoplanet astronomy in general. The Proxima b system, and any system like it, is not just scientifically interesting. It is imaginatively interesting. For most of human history, the question of whether there were other worlds beyond our own was a philosophical question answered by speculation and myth. Now, it is an empirical question answered by data. And the data say yes, there are other worlds. There is one at the very nearest star. There are thousands of them at various distances across the galactic neighborhood. The question of whether any of those worlds support life is still open, probably for a long time. But the question of whether they exist at all is no longer in dispute. They exist. They are everywhere. They are among other things right next door. And that right next door is where the strangeness of the distance reasserts itself. Because even though Proxima b is our closest known exoplanet, at 4.24 light-years away, we cannot go there. We cannot send a probe there in any reasonable timescale. We cannot study its atmosphere directly with the instruments we currently have. We can barely see its parent star clearly, because even our best telescopes struggle to resolve faint objects in the glare of nearby starlight. The nearest exoplanet is like the nearest star both, very close and completely out of reach. The Alpha Centauri system as a whole, though, contains more than just the Proxima planets. Alpha Centauri A and B, the two bright sun-like stars, are also targets for planet searches. For most of the history of exoplanet astronomy, no planets were confirmed around either of them, although several candidates have been proposed, disputed, and retracted over the years. Planets in close binary systems are harder to find and harder to confirm than planets in single-star systems, because the gravitational influence of the second star complicates the signal. For a long time, it was not even clear whether stable planetary orbits were possible around A or B at all, given how close the two stars come to each other during their mutual swing. But in August of 2024, something unusual turned up in a new set of observations. The James Webb Space Telescope, which had been deliberately pointed at Alpha Centauri A in a careful observational campaign, returned data that hinted at a faint point of light near the star, sitting at about twice the Earth-Sun distance inside the star's habitable zone. The planet was not confirmed, not firmly, but the initial detection was interesting enough to trigger an intense follow-up effort. And that follow-up effort, and the strange story of a planet that did not reappear when astronomers went looking for it again, is where the present-day Alpha Centauri story takes its most recent and most fascinating turn. The initial detection came in August of 2024, using the James Webb Space Telescope's mid-infrared instrument, known by the shorter name MIRI. The observing team was led by two researchers who would come to be named together on the eventual papers. Charles Beichman, who holds positions at NASA's Jet Propulsion Laboratory and at the NASA Exoplanet Science Institute at Caltech's IPAC Astronomy Center, and Aniket Sanghi, a PhD student at Caltech working with the same group. Both of them co-led the subsequent analysis. Both of them ended up co-first authors on the two papers that eventually reported the results. And both of them are names to remember, because the story they unpacked over the following year is one of the stranger and more interesting recent episodes in direct imaging astronomy. What Beichman and Sanghi and their colleagues were attempting to do was something very difficult in principle. Direct imaging of an exoplanet, which is what they were trying for, means actually seeing the faint light of the planet itself separate from the much brighter light of its parent star. It is not the most common way of discovering exoplanets. The method that has found the vast majority of the several thousand confirmed exoplanets in the catalogue to date is the transit method, which detects the small dip in starlight that occurs when a planet passes in front of its star from our line of sight. The transit method is indirect. You do not see the planet. You see the star, and you notice that it got slightly dimmer for a few hours. From the pattern of those dimmings, you infer the presence of the planet. Direct imaging is different. Direct imaging means actually seeing a point of light in the image that is the planet separate from the point of light that is the star. It is enormously harder because the star is typically billions of times brighter than the planet, and the two of them are separated by only a tiny angular distance as seen from our vantage point. Trying to see a planet next to a star is a little like trying to see a firefly next to a lighthouse from a distance of several miles away. The lighthouse's glare overwhelms the firefly. Unless you have a way to block the lighthouse's light very precisely, the firefly is invisible. The solution astronomers have developed is an instrument called a coronagraph. A coronagraph places a physical mask inside the telescope's optics, positioned exactly where the bright starlight would otherwise land, blocking that starlight from proceeding further. The name comes from its original application, which was blocking the sun's disk so astronomers could see the sun's much fainter corona during non-eclipse conditions. The same technique applied to distant stars lets you create an artificial eclipse, blocking the star and revealing whatever faint light might be present nearby. MIRI on the James Webb Space Telescope has a coronagraph built into it, and in August of 2024, the Beichman and Sanghi team pointed that coronagraph at Alpha Centauri A. The observations were by any account extraordinarily challenging. Alpha Centauri A is a bright star. More than that, it has a second bright star very close to it, Alpha Centauri B, which complicates the coronagraphic process because the coronagraph can only block one star at a time. The scattered light from B leaks into the region around A, making it harder to see any faint object that might be orbiting A. Beichman noted in the published results that the operations team had to develop a custom observing sequence specifically for this target, because the stars were bright enough close enough to each other and moving across the sky quickly enough that the standard JWST observation procedures were not adequate. The team built a new way to observe the system, and then they did it. And in the data from August 2024, once all of the stellar light had been carefully subtracted, they saw something. A single faint point source, well separated from Alpha Centauri A, at about twice the Earth-Sun distance from the star. The object was about 10,000 times fainter than the star itself. It was at the kind of angular separation where a real orbiting planet might reasonably sit, and it had some of the physical properties you would expect from a cool gas giant if it were a planet rather than some background artifact. The team gave it a designation S1 and began the careful work of trying to figure out what it was. The first question was whether the object was actually a planet at all, or whether it might be a background object like a distant galaxy or a foreground asteroid that happened to be aligned with the position near Alpha Centauri A. The team worked through various possibilities. They checked known catalogues of background sources in that region of sky. They examined the point source's brightness properties across different infrared wavelengths. They tried to rule out every alternative explanation they could think of, and nothing quite fit as well as the simplest interpretation, which was that they were looking at a gas giant planet, roughly the mass of Saturn orbiting Alpha Centauri A, at a distance of about 2 astronomical units. If the interpretation was correct, this would be a notable result. Not the first exoplanet ever directly imaged, which had been done before around more distant stars, but the first habitable zone planet directly imaged around a sun-like star, and the closest such target by a wide margin. The team began preparing for follow-up observations to confirm it. Additional JWST time was requested and granted. In February of 2025, they looked again, and this time they did not see anything. The candidate planet was not there. This is by itself not necessarily a problem. Faint sources come and go in direct imaging, for all sorts of reasons, many of them having to do with subtle instrumental effects rather than anything truly cosmic. The team ran additional observations in April of 2025. Again, no detection. 2 follow-up observations, both of them blank. Sanghi later described the situation with a quiet kind of puzzlement, saying that the team was faced with the case of a disappearing planet, not a phrase any astronomer relishes using in a serious publication. But there it was, with 1 detection in August of 2024, followed by 2 non-detections in early 2025. The data taken at face value looked inconsistent. The team did not give up. Instead, they did what astronomers do when the direct approach stopped working, which is to simulate the possible orbits. The planet, if it was real, had to be moving in some specific orbital path around Alpha Centauri A. That path would put the planet at different positions in the sky at different times. If the orbital period was short enough, and if the orbit was elliptical enough, it was entirely possible that the planet had moved into an unfavorable position by the time of the follow-up observations close enough to the star that the coronagraph could no longer distinguish it from the stellar residuals. The team ran computer simulations testing millions of possible orbits and asked a straightforward question. Out of the orbits that are gravitationally stable, given Alpha Centauri B's nearby gravitational influence, and that are consistent with the single detection in August 2024, how many would have been invisible to JWST in February and April of 2025? The answer turned out to be substantial. In roughly 52% of the stable simulated orbits, the planet would have been too close to the star, or in an otherwise unfavorable geometric configuration, to be detected in both of the 2025 observation windows. In other words, even if the planet really was there was about a 50-50 chance it would have been invisible on both follow-up dates simply because of orbital motion. The non-detections, rather than refuting the existence of the planet, turned out to be statistically consistent with a planet on a plausible orbit that had moved out of view. The team also incorporated an earlier candidate detection from 2019, made by a different team, using the European Southern Observatory's Very Large Telescope, which had suggested the presence of a planet at a slightly different distance from Alpha Centauri A. Taking all 4 observations together, the team argued that a single plausible gas giant planet on an elliptical orbit could account for every data point, seen in 2019, seen again in 2024, missed in February and April of 2025. The team's analysis was written up in 2 companion papers, both published in the Astrophysical Journal Letters in August of 2025. The first paper, led by Beichman, focused on the observational evidence and the orbital and physical properties of the candidate. The second paper, led by Sanghi, focused on the binary star modeling the planet and dust surge and the sensitivity analysis of the observations. Together, the 2 papers laid out the full case. If the candidate planet is real, it is a cool gas giant of roughly Saturn mass orbiting Alpha Centauri A on an elliptical path that sweeps through most of the star's habitable zone, with an orbital period somewhere between 1.5 and 2.5 Earth years. If it is confirmed, it would become the closest directly imaged planet to Earth, the first directly imaged planet in the habitable zone of a Sun-like star, and the coolest and lowest mass planet ever directly imaged. A number of astronomers in the field interviewed for various science news outlets after the papers were published described the candidate as intriguing, but not yet confirmed. Emily Rickman at the Space Telescope Science Institute was quoted noting that all data tells you something whether it is a detection or not, and that the paper was a meaningful test of what JWST's MIRI instrument could actually push to. Elizabeth Matthews at the Max Planck Institute for Astronomy was quoted calling it an exciting candidate, while also noting that there were still open questions that needed to be answered to be completely sure. And those open questions are what everyone involved is now waiting to resolve, because the team's orbital modeling produced a specific prediction. If the planet exists, and if it follows the elliptical orbit that best fits the 2019, 2024, and 2025 data, then it should reappear in a detectable position next to Alpha Centauri A in August of 2026. That is a few months from when this recording was made. The next observation window is already on the schedule. The JWST team is planning to look again. If the planet shows up where the orbital model predicts the detection will be confirmed. If it does not, the question reopens. I find this kind of story genuinely captivating, and not just for the scientific content. There is something about the process of patient simulation of taking a single ambiguous detection and a pair of non-detections and reasoning your way to a specific testable prediction for next year that captures what contemporary observational astronomy actually looks like in practice. It is not always a matter of seeing something clearly on the first try. Often, it is a matter of seeing something once losing it, and then working through the physics carefully enough to figure out where it might have gone and when it might come back. The Beichman and Sanghi team did that work. They turned a disappearing planet into a prediction. Now they are waiting, like everyone else, for the next observing window to arrive. Meanwhile, the question of whether there are other undetected planets in the Alpha Centauri system continues to drive more observations. The system is and will remain one of the most carefully studied stellar targets in all of astronomy, simply because of how close it is and how much scientific value any confirmed planet there would have. If the Alpha Centauri A candidate is real, it will likely not be the last planet found in the system. There may be smaller worlds too faint to image directly, yet that will be resolved as the next generation of telescopes comes online. The Nancy Grace Roman Space Telescope set to launch in the next few years will have capabilities that should help. The European Extremely Large Telescope under construction in Chile will as well. All of this work has been and remains grounded in one simple fact about Alpha Centauri. The system is close enough that we can study it in detail. Its planets, if they exist in the numbers that current models suggest, are or will soon be the most carefully characterized exoplanets in existence. We can resolve the system's structure. We can map its geometry. We can test specific hypotheses about its composition and evolution. What we cannot do, and what no technology we currently possess can let us do, is actually go there. And the scale of that second problem, the unbridgeable distance between knowing a system well and being able to visit it, is the subject we turn to next. The farthest thing humans have ever sent anywhere is called Voyager 1. It was launched from Cape Canaveral, Florida, on September 5th of 1977, on a trajectory designed to take it past Jupiter and then past Saturn. The physics of the launch, combined with the gravitational slingshot maneuvers at those two gas giants, were arranged so that the spacecraft would pick up speed from each encounter and continue outward with more velocity than it had arrived with. After the flyby of Jupiter in 1979, Voyager 1 swung onward to Saturn. After the flyby of Saturn in November of 1980, the spacecraft left the plane of the planets entirely and began heading roughly out of the solar system, up and away from the disk along which the planets orbit the Sun. From the moment of that Saturn flyby in 1980, Voyager 1 has been traveling uninterrupted in the same general direction and at the same general speed for 45 years. It has never fired another major maneuver. It has simply coasted using the kinetic energy imparted by the gas giants outward into the dark. Its speed is roughly 38,000 miles per hour, or about 17 kilometers per second. That sounds fast. By any earthly standard, it is fast. No aircraft can sustain such a speed. No commercial rocket in its normal flight profile matches it, except during launch. The International Space Station orbits Earth at about 17,000 miles per hour, less than half Voyager 1's cruising speed. The fastest any human being has ever traveled briefly was in the Apollo 10 spacecraft returning from the Moon, which hit about 24,000 miles per hour during re-entry. Voyager 1 has been traveling faster than that steadily for more than 4 decades. It is a very fast object. And yet, in the context of interstellar distances, 38,000 miles per hour is close to nothing. Let me walk you through what this speed actually covers in the units that matter for our discussion. In 1 hour, Voyager 1 crosses 38,000 miles. That is a significant fraction of the Earth's own diameter. In 1 day, it crosses about 900,000 miles. That is almost 4 times the distance from the Earth to the Moon. In a year, at its sustained cruising speed, Voyager 1 covers about 3.5 astronomical units, meaning the distance between the Earth and the Sun repeated 3.5 times over. That is a real distance. That is substantial. Over 4 decades of cruising, Voyager 1 has now covered more than 170 astronomical units, putting it about 170 times farther from the Sun than the Earth is. It is in interstellar space. It has crossed the heliopause, the boundary where the Sun's stream of outflowing particles gives way to the ambient interstellar medium. It is by any reasonable definition outside the solar system. As of early 2026, Voyager 1 is about 16 billion miles from Earth, and on November 15th of 2026, according to the current projections at NASA's Jet Propulsion Laboratory, it will cross a specific threshold that no spacecraft has ever crossed before. It will be at that moment exactly one light day from Earth, meaning that light itself, the fastest thing in the universe, would take a full 24 hours to travel the distance between Voyager 1 and our planet. A radio signal sent from Earth on November 15th will take a full day to reach the spacecraft. A response sent back by Voyager 1 will take another full day to return. That round trip from Earth to Voyager 1 and back will take 2 full calendar days. The project manager for Voyager at JPL is an engineer named Suzanne Dodd, and she has described the communication situation to various science journalists over the last year in terms that capture the texture of what operating such a distant spacecraft actually feels like. If she sends a command at 8 in the morning on a Monday, the response from Voyager 1 arrives around 8 in the morning on Wednesday. If there is a problem with the spacecraft and the team decides to send an instruction to fix it, they have to wait 2 days to know whether the instruction was received and carried out correctly. There is no real-time control. There is no direct observation of what the spacecraft is doing right now. There is only the patient 2-day cadence of sending and receiving across a distance that only expands with each passing month. Journalists covering the mission have sometimes described this situation as operating in slow-motion nerves, a phrase that captures the specific kind of quiet tension the Voyager team lives with. When something goes wrong with a nearby spacecraft, engineers can respond immediately. When something goes wrong with Voyager 1, they have to wait often for days, sometimes for weeks, while signals crawl back and forth across the widening gulf. The mission has had several serious anomalies over the last few years, including a computer glitch in late 2023 that scrambled the spacecraft's transmissions for months before the JPL team, working through the long delay, managed to diagnose and fix the problem remotely. That kind of repair work done across a 16 billion mile one-way signal path is a form of patience that does not really have a terrestrial equivalent. Voyager 1 is powered by a radioisotope thermoelectric generator, which converts the decay heat of a pellet of plutonium into electrical power. That power is dwindling slowly as the plutonium decays. Over the decades, the Voyager team has had to turn off instruments one by one to stay within the spacecraft's shrinking energy budget. Several scientific instruments are now dark. The team estimates the mission may be able to operate at least one remaining instrument for another few years, possibly into the early 2030s. At some point, power will drop below the threshold needed to transmit, and Voyager 1 will fall silent. The spacecraft will continue moving, of course. It will keep traveling outward at 38,000 miles per hour, but we will no longer hear from it. And the mission has faced other aging-related problems. The attitude control thrusters, the small jets that keep the spacecraft's antenna pointed at Earth, have had clogging issues in their hydrazine lines. Dodd has noted in interviews that the spacecraft no longer has any backup for certain critical systems. Everything on board is, as she put it in one interview, single string. If the remaining thrusters fail, the antenna will drift off Earth and communication will be lost. If the heaters that keep the propellant lines warm fail, the propellant will freeze, and again, the mission ends. The spacecraft, in other words, has been aging one irreplaceable component at a time for decades. The people managing it have been aging alongside it. The Voyager team at JPL now spans multiple generations of engineers from retirees in their 80s who helped design the original mission to young engineers born after the spacecraft had already left the solar system. They are keeping the machine alive together across the long generational arc. And through all of this aging and dwindling and patient repair, Voyager 1 continues moving. It continues crossing distance after distance. And on November 15th of 2026, it will pass the 1 light day mark, a milestone no human-made object has ever reached. I want to stay with that milestone for a moment, because it contains a number that matters for the rest of this story. 1 light day as a distance is roughly 16 billion miles. That is a fantastic number by any earthly comparison. It is more than 170 times the distance from the Earth to the Sun. It is far beyond the orbits of all the planets. It is deep in interstellar space. But now, let us put that number against the distance to Alpha Centauri, which is what this whole story is really about. 1 light day is 1/365th of 1 light year, roughly, meaning it takes light about 365 times longer to travel 1 light year than to travel 1 light day. And Alpha Centauri is 4¼ light years away, which means that Alpha Centauri sits in terms of light travel time roughly 1,550 times farther from Earth than Voyager 1 will be on November 15, 2026. Voyager 1, our most distant spacecraft, still has to traverse 1,500 more light days of distance before it would reach the nearest star. And Voyager 1 is not headed toward Alpha Centauri. Its trajectory is taking it in a different direction entirely. Voyager 1 is moving up and out of the plane of the planets toward a region of sky in the constellation Ophiuchus. It will not come close to any star for the next several tens of thousands of years. The closest it will get to any stellar object in the next 40,000 years is about 1½ light years, when it will drift past a faint star called Gliese 445. 1½ light years is closer to that star than we are to Alpha Centauri. But Voyager 1 will be at that point some 40,000 years into its journey, moving at the same 38,000 miles per hour long, past the possibility of any communication with Earth. It will be a silent metal object still carrying the golden record attached to its flank, drifting through interstellar space on a trajectory that leads nowhere in particular. 40,000 years is itself a number worth handling carefully. The oldest known cave paintings in Europe, some of the earliest clear evidence of symbolic thought in our species, are roughly that age. If our ancestors had somehow launched Voyager 1 at the moment they were drawing those paintings, the spacecraft would only just now be reaching Gliese 445. That is the scale of patience the trajectory demands. Whole spans of human prehistory collapse into the time between a probe leaving and a probe arriving at its closest stellar approach. And the spacecraft in question is not even headed for the nearest star. It is just drifting past a more distant one, happening to come within a few light years in passing, while the vast majority of its continuing journey takes it through empty interstellar space where nothing of interest lies for yet more tens of thousands of years beyond that. If instead, Voyager 1 were heading directly toward Alpha Centauri, the trip would still take roughly 75,000 years at its current speed. 75,000 years. The human species, anatomically modern Homo sapiens, has existed for about 200,000 or 300,000 years. Agricultural civilization has existed for about 12,000. Recorded history with writing goes back about 5,000. 75,000 years is longer than every civilization that has ever existed, combined several times over. It is a journey that no human lifetime can span, no dynasty can oversee, no political institution can sustain. If we launched Voyager 1 today toward Alpha Centauri and gave it that journey to complete, we would be asking a spacecraft to outlive every country that currently exists, every religion that currently exists, every language that currently exists, and then some. That is the speed problem translated into the terms that matter. Our fastest object has covered roughly 1/1500th of the distance to the nearest star in almost 50 years. To cover the rest would take the rest of human history replayed many times over. I want to mention the golden record here briefly because it touches on one of the quiet beauties of the Voyager mission and helps contextualize what we have actually managed to do with these spacecraft, despite the distances involved. Each of the two Voyager probes carries a copy of a gold-plated copper phonograph record inscribed with sounds and images from Earth. Greetings in 55 languages, music from various cultures, photos of people and places and natural scenes from around the world. Whale songs a baby crying the sound of a kiss. The records were intended as a message in a bottle addressed to whatever intelligence might ever find them in whatever unknowable future epoch. They are, in that sense, the farthest artifacts of Earth civilization we have ever produced. And they are riding right now on a spacecraft that will spend tens of thousands of years drifting through interstellar space without ever encountering another star system. The golden record will outlast almost everything humans have ever built. It will outlast the languages etched onto it. It will outlast the people who chose its contents. It will outlast the agency that sent it. Over the kind of timescales involved the Earth itself, will go through major geological changes while the golden record sits in the frozen dark, being slowly abraded by cosmic ray impacts, still bearing its hopeful greetings to anyone who might one day find it. Whether anyone ever does is a question no human will ever know the answer to. Voyager 1 and the golden record taken together are the fullest expression of what our civilization has so far been able to send toward the stars. And the expression honest about itself is modest. A small aging machine moving at a speed that is fast by human measures and slow by interstellar ones, carrying a phonograph record and some scientific instruments crossing one light day of distance after nearly half a century of continuous travel. That is where we are as a species in terms of our ability to physically project ourselves into the space between stars. It is remarkable in its own way. It is also, when measured against the distance to Alpha Centauri, very close to nothing. Which brings us to the question of what it would actually take to do better. What kind of engineering, what kind of propulsion, what kind of mission architecture might allow us to travel to the nearest star system in any meaningful fraction of a human lifetime? People have thought about this question seriously. There are proposals. Some of them are even in early development, but the numbers involved once you run them turn out to be every bit as humbling as the Voyager numbers are. They simply fail in different ways. And the most famous proposal of recent memory, announced in New York in 2016 by a Russian billionaire and a British theoretical physicist, is where we go next. In April of 2016, at a press conference held in New York City, the Russian-born billionaire Yuri Milner and the British theoretical physicist Stephen Hawking stood together in front of assembled reporters and announced a project called Breakthrough Starshot. The project's stated goal was to send a fleet of tiny spacecraft to Alpha Centauri within the lifetimes of people who were alive to hear the announcement, not in 75,000 years, but in about 20/10 of a human lifespan. The announcement was by the standards of serious interstellar proposals striking. It was also, by the standards of engineering, extremely ambitious, bordering on aspirational. Whether it will ever actually happen is a question that remains open 10 years later. But the concept is worth walking through because it captures both what we might plausibly do and what the physical limits actually are. The idea of Breakthrough Starshot is to throw out entirely the model of interstellar travel that relies on traditional chemical rockets or even near-future propulsion technologies like nuclear thermal or ion drives. A chemical rocket cannot take you to the stars. The math simply does not work. To reach Alpha Centauri in any reasonable time frame, even a few hundred years, you would need to carry an amount of propellant that vastly exceeds the carrying capacity of any rocket we know how to build. You would need to build a rocket that was almost entirely propellant with essentially no payload, and even that would not be enough. The tyranny of the rocket equation, as aerospace engineers sometimes call it, makes this approach a dead end for interstellar travel. Nuclear propulsion does somewhat better depending on the specific design. A nuclear thermal rocket, which uses a nuclear reactor to heat hydrogen propellant, could improve the efficiency over chemical rockets by a factor of several. A fusion rocket, if we could build one, could improve efficiency further still. But even the most optimistic fusion drive concepts would get you to Alpha Centauri in something like centuries, not decades. Your great-grandchildren might see the mission return data if you launched it now. Most of the engineers who worked on it would be long dead. The project would span generations. Whether that counts as interstellar travel in any meaningful human sense depends on your definition. Breakthrough Starshot takes a different approach. Instead of carrying the propellant on board, the project proposes using a ground-based laser array to push the spacecraft from Earth. The spacecraft itself would be tiny, on the order of a gram in mass, with most of the mass in a thin reflective sail, a kind of light sail that catches the light from the laser and is pushed forward by photon pressure. The laser would be enormous, built on the ground somewhere in a high-altitude dry location. A phased array covering perhaps a square kilometer of surface firing for a few minutes at full power. During those few minutes, the combined laser energy striking the light sail would accelerate the tiny spacecraft to about 20% of the speed of light. Once the laser shut off, the spacecraft would continue coasting at that speed, no longer accelerating, covering the distance to Alpha Centauri in a little over 20 years. 20% of the speed of light, 200% faster than 20,000 miles per second. Let that number settle for a moment. It is by any standard an astonishing speed, roughly 1,000 times faster than Voyager 1 currently moves. At that speed, the trip across one astronomical unit from the Earth to the Sun would take about 40 seconds. The trip across the solar system from the Sun to Pluto would take about a day. The trip to Alpha Centauri would take about 20 years. The advantages of this architecture are real. The spacecraft carries no propellant, so the rocket equation does not apply. The propulsion is supplied externally by the laser array, which stays on Earth and can be enormous. The spacecraft itself can be tiny and light, which means many of them can be launched cheaply in sequence. Each mission sends dozens or hundreds of gram-scale probes toward Alpha Centauri, any of which might survive the journey and arrive intact. Redundancy is built in. The disadvantages, however, are also real, and they are where the engineering becomes difficult. The first problem is the laser array itself. Building a coherent laser array of the required power at a scale covering something like a square kilometer of Earth's surface is well beyond anything we have currently constructed. The array would need to deliver something like 100 gigawatts of combined laser output during its acceleration phase. 100 gigawatts, for context, is comparable to the total electrical output of several dozen large nuclear power plants focused into a single coherent beam. We have nothing like that now. We are in 2026, years away from even small-scale demonstrations of the underlying technologies at much lower power. The second problem is the light sail material itself. At 20% of the speed of light, Any imperfection in the sail, any point where the laser energy is absorbed rather than reflected, produces enormous heating, more than enough to vaporize the sail. The sail material would need to reflect essentially all the incoming laser energy with extremely low absorption. Materials that can survive such intense illumination, while also being thin enough, light enough, and reflective enough to be useful, are at the edge of what is currently known. Research is ongoing. Progress has been made. But producing such a sail in the quantities required for an actual mission with the quality required to survive the full laser pulse is still more concept than reality. The third problem is communication. Assume you manage to build the laser launch, the light sail accelerate the spacecraft, and have it arrive at Alpha Centauri 20 years later in working condition. How do you hear from it? A gram-scale spacecraft does not have room for a large high-gain antenna. It does not have room for a high-wattage transmitter. Getting any signal back to Earth from Alpha Centauri from a gram-scale source requires either an enormously sensitive receiver on the Earth's end, or some kind of clever optical communication scheme, where the spacecraft uses a small laser of its own to send brief pulses of data homeward. Either way, you have to overcome the fundamental difficulty that a small transmitter at 4 light-years cannot produce a signal that reaches Earth without being completely overwhelmed by the ambient noise of Alpha Centauri itself, which sits in almost the same direction as the spacecraft from our vantage point. The communications problem is in some ways as hard as the propulsion problem. The fourth problem, less often discussed but present, is what the probe would actually do when it arrived. At 20% of the speed of light, the spacecraft flashes through the Alpha Centauri system in a matter of hours. There is no way to slow down. Bringing the probe to a halt at Alpha Centauri would require as much deceleration as the initial acceleration, and there is no laser array on the far end to do the braking. So the mission is a flyby. The spacecraft takes whatever data it can during its brief pass through the system, and then continues onward into the void beyond, no longer able to observe anything useful. A few hours of observation, followed by a 2-decade radio lag before the data reaches Earth. That is the limit of what any flyby mission of this type can return. Breakthrough Starshot, then, is a beautiful and ambitious proposal that turns out to be harder than it first appears. It is not impossible as far as anyone can tell. The underlying physics is sound. The engineering challenges are real but do not obviously violate any fundamental laws. If the project continues to be funded, and if the necessary basic research into lasers and sail materials continues to make progress, then, in some decades, maybe a fleet of gram-scale probes might actually be launched. And if they are, and if they survive, then we might, within a human lifetime, receive the first close-up signals from the Alpha Centauri system. Might. The whole proposal sits inside an interlocking set of conditional clauses. None of the conditionals are obviously impossible. None of them have been demonstrated either. The project is, as of the mid-2020s, still very much in its early research phase. Whether it evolves into an actual mission, and on what timescale, nobody can say with confidence. What the project does establish clearly, however, is what the lower bound of interstellar travel looks like. At 20% of the speed of light, you can reach Alpha Centauri in 20 years. That is the optimistic scenario, assuming everything works. Going faster than that, to get there in less time, requires even more aggressive technologies, most of which are even more speculative. At half the speed of light, which no remotely plausible current technology can achieve, the trip would take around 8.5 years. At the speed of light itself, which is a hard physical limit that cannot be exceeded, The trip would take 4¼ years the light travel time. You cannot go faster than light, so 4¼ years is the absolute floor for any journey from here to Alpha Centauri under any conceivable propulsion technology. The actual limit of how quickly you can physically visit the nearest star set by the laws of physics themselves is a little over 4 years one way, and that floor is for a one-way trip with no payload, no return mission, no ability to stop. For a crewed mission with a human-rated spacecraft, with life support for years of travel, with the need to decelerate at the destination and spend time in the system and come home again, the real timescales balloon into centuries or more. No current or near-term technology can carry a human to Alpha Centauri. Not in a lifetime, not in a generation, not in any time frame that would let the traveler's original civilization still exist when the return signal came back. This is the hard truth at the center of our story. The nearest star, which we can see with our eyes, which we can study with our instruments, which we can map and measure and photograph and simulate, is functionally unreachable by human beings, not because of a temporary limitation we will overcome with another few decades of engineering, because of the physics of distance combined with the physics of propulsion, combined with the physics of how much human mass and life support and fuel you have to move across how much empty space. The problem is not technological at its root. It is fundamental, woven into the laws of the universe. Any realistic estimate of the speeds and energies involved with any plausible propulsion system ends with decades or centuries of travel time for anything other than gram-scale probes, and even the gram-scale probes require technologies we do not currently have. I want you to let this land gently. Not as a sad conclusion, but as a true one, because there is something honest about accepting it. And I think the listener tonight is here because the honesty of this kind of thinking is in some sense what brings you back. We will probably never visit Alpha Centauri. Our species, if it continues to exist, might someday develop the capability. That capability is not obviously impossible, but it is distant enough that speaking about it with certainty, one way or the other, would be dishonest. For now, for all the generations of humans currently alive, and probably for all the generations of humans born for a long time yet to come, the nearest other sun is something we look at and not something we go to. And that is okay. That is in its quiet way enough. We have the looking, the studying, and the knowing. We have the slow accumulation of facts about the system, the 3 stars, the planets, the candidate planet around Alpha Centauri A, the confirmed planets around Proxima, the orbital dynamics, the stellar properties, the age, the composition, the behavior. We know more about Alpha Centauri today than Thomas Henderson, measuring his first parallax at the Cape of Good Hope in the 1830s, could have imagined would ever be knowable. And that accumulated knowledge gathered by generations of telescopes and astronomers and patient observers continues to deepen every year. The 4¼ light-year distance will not shrink. Our reach will not suddenly jump. Voyager 1 will continue drifting silently in the wrong direction. Breakthrough Starshot will continue its slow research and development arc, possibly toward an eventual mission, possibly not. But the star itself will continue burning steadily in the southern sky, as it has for billions of years and will for billions more. It is not going anywhere, it is not waiting for us, and it is not demanding our presence. It simply exists, bright and amber white in the southern sky, as the closest of our stellar neighbors visible from the southern half of the planet, hidden below the horizon for the northern half. A quiet light, a patient one, nothing we can reach, and nothing that asks to be reached. Let us hold that image for a while. the star steady in the southern sky, the distance unchanging, the knowledge slowly growing. Our species here on a small planet looking up at it, knowing what it is, knowing we cannot go there, knowing that the knowing itself is a kind of intimacy. There is a way to hold that intimacy that does not feel like loss. And that is where the rest of our drift takes us. Let us sit with the full shape of what we have been describing, because the shape deserves a moment of its own before we turn softer. A bright star in the southern sky, the third brightest point you can see at night if you are south of the equator to see it at all. 4¼ light years away. A triple stellar system, 2 sun-like stars locked in an 80-year orbital dance, and a small red dwarf drifting around them in a much longer, much lazier circuit. At least 3 confirmed planets around the red dwarf, one of them roughly Earth-massed and sitting in the general distance range where liquid water could in principle exist on the surface. A strong candidate for a 4th planet, a cool gas giant circling Alpha Centauri A, in its habitable zone currently awaiting confirmation in observations that will happen a few months from when this recording was made. And all of it, every single world, every single star, every single detail of what goes on in that system, sitting at a distance that our fastest spacecraft would cross if it were aimed that way, and it is not in roughly 75,000 years. That is the honest accounting. It is not a sad accounting, though it can feel that way if you approach it from a certain angle. It is simply what the numbers say translated into the units of human life. The nearest other sun, visible and known and carefully measured, is beyond the reach of any journey we currently know how to attempt. Not a little beyond, and not a frustrating but potentially solvable kind of beyond, but beyond in a deeper way. Beyond in the sense that even if every nation on Earth redirected their entire industrial capacity toward building an interstellar mission, and every breakthrough imagined by the most ambitious engineers were realized simultaneously, the best we could plausibly manage would be to send gram-scale probes in a 20-year flyby, arriving long after most of the people who started the project had aged out of their careers, gathering a few hours of data, and then continuing silently into the void beyond while the world waited decades more for the radio signal to return. There is no crewed interstellar mission on any reasonable near-term horizon, no ship of explorers, no extended stay, no return trip, no children born on Alpha Centauri worlds, no retirement settlements orbiting Proxima. Those futures which science fiction has been imagining for more than a century remain firmly in the territory of imagination. The physical constraints are not ones that clever engineering will overcome in a decade or a generation. They may not be overcome ever for creatures as fragile and short-lived as we are. I think the honest response to all of this is not disappointment. It is something closer to a specific kind of calm. The universe is arranged the way it is arranged. Distances are what they are. The speed of light is not a problem we invented. It is a feature of the space-time we live inside. And within that space-time, we happen to exist on a small planet that sits 4¼ light years from its nearest stellar neighbor. That neighbor is not hidden from us. It is not lost in the dark. It is right there, visible from the southern half of our planet, studied in detail by telescopes on the ground, and in orbit monitored by ongoing observation campaigns mapped in its basic structure, theorized about in specific ways. We know a great deal about Alpha Centauri. We will know more. The knowledge is not bounded by the distance, as long as we are willing to settle for remote observation rather than personal visit. And remote observation is frankly an astonishing thing to be able to do. Think about what is actually happening when a telescope like JWST turns toward Alpha Centauri. How photons are leaving the surface of those stars and their surrounding environments, traveling across 4.25 years of empty space, arriving at a segmented gold mirror, floating at a Lagrange point 1,000,000 miles from Earth, being focused onto sensitive infrared detectors, being converted into digital data, being relayed back to Earth, and being analyzed by researchers who use the patterns in that data to reconstruct what was happening in the Alpha Centauri system years ago. The whole chain of events is a quiet collaboration between the physics of light, the engineering of instruments, and the patient intelligence of people who spend their careers studying stars they will never approach. Alpha Centauri will continue burning. That is the thing I want to hold on to as we move toward the final stretch of this drift. The star will continue. The binary dance of A and B will continue. Proxima will continue its slow, far orbit around them. The candidate gas giant, if it exists, will continue sweeping through its elliptical path on its approximately 2-year period visible in August of 2026. If the orbital models are right invisible, if they are wrong either way, following the laws of gravity exactly as it has been, doing since long before our species existed. Whether we ever build breakthrough Starshot, whether we ever send probes, whether we ever manage to characterize the atmospheres of the Proxima planets, whether we ever confirm the Alpha Centauri A candidate, whether we ever discover additional worlds in the system, whether we ever manage interstellar travel in any meaningful sense at all, the star itself will not care. It will continue doing what it has always done. It will burn through its hydrogen heat. Its immediate surroundings produce its small stellar wind, hold its planets in their stately loops, participate in its long gravitational relationship with its two companions. The star's life is not entangled with ours in any way that matters to the star. It does not know we exist. It does not respond to our attention. It existed for billions of years before anyone on Earth ever noticed it, and it will exist for billions of years after our species is gone. And yet we do notice it. That is the part that matters for us. A bright amber-white point in the southern sky, known by name, known by type, known by age, known by its gravitational relationships with its neighbors, known for hosting at least one rocky planet, and probably several. A star that Thomas Henderson first measured in the 1830s, that Robert Innes identified as a triple system in 1915, that Guillaume Anglada-Escudé's team found planets around in 2016, that the James Webb Space Telescope has been peering at in detail in the 2020s. 2 centuries of careful attention accumulating a detailed picture of a system we can see but cannot visit. A system we have in the and befriended from across an unbridgeable distance. There is something almost medieval about that arrangement when I think about it carefully. In older European traditions, there were relationships you maintained with people and places you could never actually reach. A pilgrim who dreamed of a shrine they would never visit. A scholar who corresponded with colleagues on other continents, trading letters that took months to arrive. A poet writing about a city they had only ever read about. These relationships were real even though they were entirely mediated by distance and imagination and occasional slow communication. The Alpha Centauri system is the cosmic equivalent. It is a place we will never stand on, whose details we will never touch, whose textures we will only ever know through the photons that cross the gulf to reach us. And yet, we keep learning about it. We keep paying attention, we keep sending telescopes toward it, and the relationship persists. If any of this is starting to feel slow, that is because it is meant to. The weight of what we have been describing is not a fast weight. It is not a shock. It is the kind of weight that settles gradually the way cold water settles into warmer water until the whole pool reaches the same temperature. 4¼ light years is not a fact you absorb in one sentence. It is a fact that takes time to feel. The same for 75,000 years of travel time. The same for the idea that the nearest other sun is something our species, as currently constituted, will not be visiting. These are slow facts. They settle at their own pace. Take whatever time you need with them. The rest of the drift will meet you where you are. The star, meanwhile, will keep burning in the southern sky. It has been doing that for billions of years already. It will continue doing it for several billion more. At any given moment of the night, if you are in the right part of the world to see it, it is up there burning its steady yellow-white light. Its light crossing the dark between us, one photon at a time, arriving at your eyes 4 years after it left. Whenever you look at it, you are looking at a small piece of your own recent past. The star you see tonight is the star of 4 years ago. The star you will see a decade from now will be the star of 6 years from now. That lag is fixed. That lag is built into the geometry of our relationship with Alpha Centauri. And that fixed lag, that permanent 4-year delay, is where I want to take you next. Because there is a kind of tenderness inside that number if you let yourself sit with it. And the tenderness is the shape this story takes when you carry it from the telescopes and the propulsion concepts and the hard math of unreachable distance back into the small and specific world of the person who is listening to it right now. You here drifting, that is where we are going. Think about where you were 4 years ago. Not in some elaborate autobiographical way. Just briefly. Think about the house you lived in, the job you had, the people you saw most often. Think about a small, ordinary thing that was true about your life then and is not true now. A habit you had, a cup you drank from a walk you used to take. 4 years is not a long time by the measure of a whole lifetime, but it is long enough to have become a slightly different person. You have seen different weather. You have met new faces and lost touch with old ones. You have had conversations and illnesses and small good surprises. Your body has replaced many of its cells. Your memory has rearranged itself quietly, the way memory always does, emphasizing some things and letting others fade. 4 years ago, you were you, but a slightly earlier version of you on a slightly earlier day, under a slightly earlier sky. And during all of that change, all of those 4 slow calendar years passing over your life, a beam of light was traveling through space toward your eyes. A specific beam from a specific star in the specific direction of the southern sky. The beam left Alpha Centauri's surface during a moment you probably do not remember, on a day that is now deep in your personal past. It has been crossing the dark between stars without interruption ever since. It has covered about 25 trillion miles in that time, moving at the full speed that light can move, not slowing, not deflecting, not losing its cargo of information. And now tonight, if you are in the southern half of the world, and you look up, that beam arrives at your eyes. You catch the star as it was 4 years ago, not as it is now. That is not possible. The light that leaves Alpha Centauri now will not reach you for another 4 years. You will be older by then again. The you who finally sees that light will be a further transformed version of the you who is listening tonight. And the stream of light continuous will keep delivering you pieces of the stars past forever, always on a 4-year delay, always arriving a little after it happened. There is a strange intimacy in that. The star, by the simple geometry of its distance, is always sending us news from a recently past version of itself, and we receiving that news are always a little behind. The two of us, the star and you, are connected by a slow cable of photons, each one carrying an earlier moment. Every time you look, you are looking at a version of Alpha Centauri you have not yet caught up to. You are always 4 years behind the present of that star. You will always be 4 years behind. No telescope, no instrument, no technology will ever let you see Alpha Centauri as it is exactly now, because the very concept of now breaks down across distances like this. Alpha Centauri's now and your now are not things you can align. They can only be approximately related by the slow passing of light. I want you to sit with that gently, because I think there is something quietly warm about it once you let it settle. The distance between us and the nearest star is large enough that it cannot be crossed, but it is also small enough that light can cross it in a single 4-year stretch. That is a human span. It is the length of a college education, the length of a presidential term, the length of the interval between a child being born and being old enough to have coherent memories. 4 years is a personal unit, and the light from the nearest other sun arrives continuously on exactly that personal unit of delay, not on a scale so large that you cannot relate to it, on a scale you know intimately from your own life. The same is not true of most of the universe. When you look at a distant galaxy, you are looking at millions or billions of years into its past timeframes that have no relationship to any unit of your own life. You cannot intuitively feel a galaxy's 100 million year lag, but you can feel Alpha Centauri's 4-year lag because 4 years is a span that fits inside your own recent history. You know what 4 years feels like. The star is sending its light across that familiar stretch of time. The star is in that specific and narrow sense only slightly behind the present. When you look toward the southern sky, if you are able to see Alpha Centauri, you are in a specific kind of communion with a star whose light has been keeping pace roughly with your own life. The photons you see tonight left the star when your life was slightly different. You have walked through the years it took them to arrive. They have been traveling the whole time you have been living. You and the star share a small, specific geometrical relationship. Nothing dramatic, nothing mystical. Just the plain physical fact that light takes 4 years to cover that distance, and during those 4 years, both of you, in your respective ways, have been continuing. And the star will keep continuing. It will be there tomorrow night and next year, in 10 years, in 50 years, in 100 years, in 1,000, in 100,000, in 100 million, in a billion. Your life is a small flicker against its life. But during the brief stretch, when you and it overlap, you get to share this slow 4-year exchange of light. Every night, you look up. If the conditions are right, the exchange is happening. You cannot visit, and you do not need to. The looking is the relationship, and the looking is enough. I want you to feel right now, wherever you are, how small the world can become when you settle into it. Your room probably somewhere dark, probably, with something soft around you. Your body slowing down, breath getting a little longer, a little quieter. The voice in your ear describing a star you may not have thought about much before, or may have thought about a great deal. Beyond your room, the larger world, going about its various activities, none of which particularly need your attention right now. And beyond the world, the sky. The southern part of the sky, with its particular star burning there, whether anyone sees it or not. You are in a sense held by several things at once, by the room you are in, by the familiar gravity of the planet you live on pressing you gently into whatever surface you are resting against, by the galaxy which contains the sun, which contains the Earth, which contains you, by the larger relationships of stars to each other, including the relationship between our Sun and Alpha Centauri. which happened to put those two suns in a specific nearby configuration. By the ongoing flow of light from that southern star, which right now, as you breathe, is reaching the top of your planet's atmosphere, some of it bouncing, some of it absorbed, some of it reaching observatories whose instruments are open, some of it, if you were in the right part of the world, reaching your eyes. You do not have to go to the star. You do not have to cross the distance. You are simply, by being where you are already, in a relationship with the nearest other sun. The relationship has been going on since you were born. It will continue until you stop being. It is not a relationship that asks anything of you. It just is. This is, I think, the quiet piece at the center of all the numbers we have been walking through tonight. 4.25 light years, 75,000 years of spacecraft travel, 2 days of round-trip communication with Voyager 1, starting in November of 2026, 16 billion miles between Earth and our farthest probe, 170 astronomical units of interstellar space traversed by Voyager 1 so far, with 1,500 more light days still to go before it would be at Alpha Centauri, if it were even heading that way, which it is not. All of those numbers are enormous. All of them describe the particular unreachability of the nearest star, and yet running underneath all of them, there is this small warm fact. The light from that star is already here on your planet on any clear southern night, arriving at your eyes whenever you look. The unreachable thing is also in the way that actually matter's already present. You can sleep on that. You can rest on that. The star does not need you to go to it. It does not need anything from you at all. It simply continues steady and amber white in a corner of the sky, carrying out the long, slow business of being a star, participating in its old gravitational dance with Alpha Centauri B and its more distant companionship with Proxima, holding its at least 3 confirmed planets and probably its 4th in their orbits, emitting its steady outflow of light across the 4.25 light-year gap between its location and ours. You are small, the distance is large, and the physics is what it is. And inside all of that, you are tonight here. Warm, probably held by whatever is holding you, breathing slowly, listening to a voice describe a star and its distance and its planets and its long history of human attention. The voice is going to soften in a few minutes. The voice is going to get quieter. The voice will eventually stop, and what will be left will be the dark and your breath, and whatever dreams come next. Before that happens, I want you to feel the shape of what we have built tonight. A star, a system, a distance, a history of measurement, a set of planets, a pair of recent scientific breakthroughs, a spacecraft that will be 1 light day from Earth in November of 2026, a proposal to use lasers to send an gram-scale probes across the gap in 20 years, a set of hard physical limits on how fast and how far humans can send themselves in any useful time, a relationship with the nearest star that is built entirely of light, entirely of observation, entirely of distance maintained and respected, rather than crossed. That is the shape of the story. And inside the story, there is you listening to it, probably on the verge of sleep, probably with your eyes closed, probably with a soft hum of whatever device is playing this voice in your ears, probably with the knowledge that the world will keep going while you rest, that the star will keep burning while you rest, that the light will keep traveling while you rest. Nothing needs your attention for the next several hours. Nothing requires you. The universe will continue perfectly well without your participation until morning. Let it. Let the star burn. Let the light travel. Let the distance be what it is. Let yourself sink slowly into the soft dark of the room you are in, while the universe carries on its vast, slow business beyond the walls. You are allowed to rest. you are allowed to stop holding the story. The story will still be here tomorrow and every night after that, as long as there is a southern sky and someone with eyes to look at it. The nearest star is 4¼ light years away. You are here wherever here is. Both facts are for tonight enough. We have walked together through a lot tonight. A star first measured by a Scottish astronomer in 1839, who doubted his own data and almost let someone else have the credit. A system of 3 stars, 2 of them, sun-like and bound to each other in an 80-year orbital dance. The third, a small red ember, orbiting them at a huge distance on a period of hundreds of thousands of years. A collection of planets including one Earth-massed world discovered by Guillaume Anglada-Escudé's Pale Red Dot campaign in 2016, and a gas giant candidate around Alpha Centauri A, first spotted by Charles Beichman and Sanghi's team in August of 2024, then missed in follow-up observations in early 2025, now awaiting another check in August of 2026. A spacecraft named Voyager 1, launched on September 5th, 1977, cruising at 38,000 miles per hour since its Saturn flyby in November of 1980, due to become the first human-made object to reach 1 light day from Earth on November 15, 2026, in a few weeks from when this recording was made. A proposed mission called Breakthrough Starshot, announced in New York in 2016 by Yuri Milner and Stephen Hawking, which would use a ground-based laser array to push gram-scale probes across the 4¼ light-year distance in about 20 years if it ever actually gets built. And a project manager at NASA's Jet Propulsion Laboratory, Suzanne Dodd, keeping Voyager 1 alive across the widening Gulf, working in what the press has sometimes called slow-motion nerves, sending commands that take a day to arrive and another day to be answered. That is the shape of what we have covered. It is a lot of specific information knotted together around one central fact. The nearest other sun is 4¼ light years away, which means it is right there and completely out of reach at the same time. We can see it. We cannot visit it. We know a great deal about it. We will learn more. And nothing about that knowledge will bring the star any closer in any physical sense. The relationship we have with Alpha Centauri will remain for the foreseeable future. A relationship of looking, not a relationship of going. I think that is okay. I have been saying that throughout this drift, and I mean it. There is nothing inherently sad about the distances in the cosmos. The distances are just the distances. They are set by the physics of the universe we happen to live in, and they are not going to change. What can change is our willingness to sit with what those distances mean without feeling diminished by them. The universe is enormous. We are small. We live on a small planet orbiting a small star with the next nearest small star sitting 4¼ light years away. These facts do not demand anything from us. They do not ask us to feel small in any way that causes pain. They simply are the facts. And within those facts we have room to do what our species has always done, which is to look and to study and to wonder and to pay patient attention. If you have been here with us this long, thank you. Genuinely. Cosmic Drift is a small channel made for nights like this, for people who want the cosmos to be part of their going to sleep. Every person who stays, who listens, who lets the voice carry them through the slow unfolding of some distant corner of astronomy is what makes this possible. If you have enjoyed drifting tonight, the gentlest thing you can do is hit the like button and subscribe to the channel. It is a small gesture. It tells the recommendation algorithms that what we do here is worth suggesting to other people who might need it. We are not asking for anything more than that. If you have already subscribed, thank you. That too means a lot. Before the voice goes quiet, let me leave you with one last image. Somewhere on Earth right now, in the southern half of the planet, it is nighttime. The sky above some stretch of ocean or desert or forest is dark and clear. And somewhere in that dark southern sky, a bright amber-white point is hanging low above the horizon, as it has been for hundreds of millions of nights long before anyone on the planet had a name for it, and as it will continue to do for billions more nights long after our species is gone. The point is not a single star. It is three, though you cannot see them as separate from here. The largest one is very much like our own sun. The second one is slightly smaller and slightly cooler. The third one is a small red ember, too faint for the naked eye hiding nearby. Around one of them, at the very least, there is a world not entirely unlike Earth orbiting in the right distance range for liquid water whipped by the flares of its parent star. Around another, there may be a gas giant. We will try to confirm in a few months. All of it 4¼ light years away. All of it completely ours to study and completely out of our reach. All of it steady and indifferent to whether we look or not, carrying on its slow business in a corner of the galaxy that we happen to be able to see under southern skies on clear nights. The star is still burning. The binary is still dancing. Proxima is still drifting around them in its long, lazy circuit. The light from all of it leaving them tonight will reach some lucky observer in the year 2030. We are not that observer. The US of 2030 will be. And the US of tonight here in the present, watching the stars of 4 years ago, arriving gently at our eyes, gets to sit inside this quiet moment while the universe does what it has always done, which is to keep going. Sleep well. The star will be there in the morning. So will you. Thank you for drifting with us.